Good morning, everyone. I am Edwin Jane M. Dolero, and we are a group 20, and I will tackle about geometry. What is geometry? Geometry is there is no branch of mathematics, however abstract, which may not someday be applied to phenomena of the real world. Geometry is a branch of math that studies shapes, size, and spaces. It helps us understand points, lines, angles, and form like circle, triangles, and squares. It is used to explain how objects fit together in the world around us. And next is the Skull of Munch. Geometry has changed in popularity over time. It was very strong in ancient Greece but declined when Rome fell. It grew again under Islamic scholars and during the Renaissance. In the 16,000s, it seemed ready for a new era, but then it was ignored for almost 200 years as other areas of math became the popular. Britain tried to bring back the old style of geometry Euclid works, but did not make new discoveries. Munch and Carnot helped revive interest in geometry during the French Revolution. The real strong comeback of geometry happened in the early 18,000s and last and Munch students at the École Polytechnique helped push geometry forward. They used geometry in many fields like engineering, teaching, and physics, and many studied geometry simply because they love it. Charles Dupin, 1784 to 1873, used geometry to improve chip design and created training programs for technical students. He is famous for his work on surfaces, especially for introducing the idea of the cyclide. Theodore Oliver, 1793-1853, made physical geometry models to help people better visualize shape and concept. His work inspired the creation of mini geometry model collections, later supported by Felix Klein. Jean-Baptiste Bayot, 1774 to 1862, mostly known as a physicist, continued Munch's teaching style by using geometry to visualize and understand both physical and mathematical problems. Lastly, Charles Joel Briachon, 1785 to 1864, a student of Munch, rediscovered Pascal's forgotten theorem. He showed that is a hexagon drawn inside a connect. The intersection points of opposite sides lie on a straight line. John Victor Panselet, 1788 to 1864, a student of Munch and soldier in Napoleon's 1812 campaign, became the founder of projective geometry. While imprisoned, he wrote an analytic geometry treatise, though it was published only in 1862 to 1864. His major work, Trait des Propriétés projective this figure, 1822. Shift of synthetic geometry, Panselet introduced the principle of continuity, which allowed geometry truths to remain valid even when figures extend to infinity or became imaginary. This led him to use the ideal points and imaginary points such as two circular points at infinity common to all circles. He also helped formalize perspectives, projectivities, poles, polars, and duality in 1820 to 1821. He and Branchon proved the nine-point circle theorem, later discovered by Feuerbach in 1822. Panselit ideas established the foundation of the complex projective plane and greatly shaped 19th century geometry. And Michael Chasles, 1798 to 1880, also from the École Polytechnique, continued and expanded Poncelet work in projective geometry. He became professor of machine technology in 1841 and later held the higher geometry chair at the Sorbonne starting in 1846. Chasles emphasized the importance of cross ratios and harmonic ratios of 4 points or lines and showed that these remain invariant under projective transformation. His influential work include Upper Q History 1837 and Trait de Geometry Superior 1852 where he promoted rather the use of directed line segments. Later in life, he founded enumerative geometry, which counts the number of geometry configurations and satisfy algebraic conditions. He developed the principle of correspondence, making him one of the last major French projective geometers of the 19th century. Synthetic metric geometry of Steiner. Jacob Steiner, 1796-1863, was considered the greatest synthetic geometer of modern times. He avoided analytic geometry and preferred pure geometric reasoning. Using only synthetic methods, he proved major results such as the theorem that a third-degree surface contains exactly 27 lines. He also proved that all Euclidean construction can be done with a straightage alone if one fixed circle is given. Steiner's name appears in many geometric ideas from the 19th century. One example is the Steiner points, formed when 6 points on a conic are connected in all possible ways to create Pascal's line. These lines intersect in 20 Steiner points. Steiner also discovered ideas related to inversive geometry where a point P and its inverse P is the one satisfy a distance relation with respect to our circle. The center of the circle has no inverse leading to an interesting paradox. Steiner did this work but never published it. Inverse geometry became important because it transforms circles and lines in special ways. Circles not going through the center become circles after inversion, while circles through the center become straight lines. A key property is that inversion preserves angle. It is conformal. Angle-preserving transformations in space are rare, as Joseph Liouville (1809 to 1882) prove only inversion and similarity congruency transformation are conformal. Because Steiner did not publish his inversion rather ideas, others later discovered them, one being Lord Kelvin 1824 to 1907, who applied inversion to physics in 1845. If the inversion center is at the origin, the inverse of a point x, y is given by formulas using the radius a. These equations later inspired Louis Cremona 1830 to 1903 to study more general coordinate transformation. In 1863, he published the theory of what are now called Cremona transformations, and he later generalized them to three dimensions. That is the example of in sa baba is x to 1 equals a raised to cube x over x squared plus x squared, and x1 equals x squared y over x squared plus x squared. Systematic non-metric geometry of Bondstand, Steiner's Systematic Equivalence 1832, described projective geometry using metric ideas. Later, von Stad 1798 1867, a former student of Gust created a new approach in his geometry, der Lage. 1847, he built projective geometry without using distance or numbers, using instead the cross, ratio, and harmonic sets as the foundation. His work showed that projective geometry could exist as a pure non-metric geometry, and that distance could be added later if needed. This idea inspired others, like 1834-1886, explored adding measurement to non-metric angle geometry, and Cayley later developed the most influential explanation of how to define a metric within projective geometry. Analytic geometry, Julius Placher 1801 to 1868, became the first major specialist in analytic geometry, although he started with synthetic geometry. A conflict with Poncelet led him to focus on analytic methods. He believed algebraic techniques were better than the purely geometric style of Poncelet and Steiner. Placher's influence remains through Placher, a bridge notation in coordinate geometry. During the early 18,000s, mathematicians like Georgon and Gabriel Lame noticed that analytic geometry involved long and difficult algebra, so they can created shorter notations. For example, Lame wrote the family of circles passing through the intersection of two given circles simply as MC plus MC equals 0. Mathematicians like Gorgon and Placher tried to simplify analytic geometry by using shorter notations. They replaced long equations with forms like C plus AC equals 0 or C plus UC equals 0, a method sometimes called lambdalizing. Lame began the study of one parameter families using the abbreviate style, but Placher expanded in the most between 1827 and 1829. Placher used this notation to explain the Cramer-Eucler paradox. He showed that if you choose 14 points and try to find a quartic curve through them, you can express is of q plus qy equals 0, where q and q thus are two different quartic curves passing through 13 of the points. The parameter is chosen to the 14th point also lies on the curve. Surprisingly, q1 to qn plus q share not only those 13 points but also the full set of 16 intersection points of q and q dash. This means that any set of 13 of those 16 special points determines the same 3 associated points, and choosing 14 or more points from that set will not determine a unique quartic. This is a paradox. Normally, 14 random points should define one quartic, but points in this special configuration do not. Placher showed that for any chosen set of points, there exist extra dependent points such that any curve of degree passing through the original points must also pass through these additional points. He also created a dual version of his theorem and extended the ideas to surfaces in three dimensions. In his influential work, Analytic Geometry, Interline, Placher raised the shortened notation of Lame and Gergon to a guiding principle. In the second volume, 1831, he essentially rediscovered homogeneous coordinates, a system already invented earlier by Feuerbach, Mobius, and others. Mobius, in his 1827 work The Barycentric Calcul, introduced barycentric coordinates by assigning masses to the vertices of a triangle so that their balance points represent the coordinates of a point. And homogeneous coordinates allow geometry to become more algebraic, but Plucker went further. In 1829, he introduced a new idea. The coefficients of a line equation could themselves be treated as the homogeneous coordinates of a line. Just to represent a point, this meant points and lines could be described in a perfectly parallel way. By rewriting the equation, Plucker showed that it could represent either all lines through a fixed point or all points on a fixed line, depending on which set of symbols is treated as constants. This reveal the analytic foundation of duality, the principle that every theorem about points has a corresponding theorem about lines. Plucker further showed that any plane curve can be viewed in two ways, as a path trace a moving point or as envelope of moving line. However, the degree of a curve as a set of points, its order may differ from the degree is a set of tangent lines in class. In 1834, Plucker published four famous equations relating curve order, class, and singularities, laying essential groundwork of projective geometry. Mobius introduced baryocentric coordinates by treating a point as the center of gravity of masses placed at the vertices of a triangle. He also classified geometric transformations such as congruence, similarities, affine transformation, and collineation, and encouraged studying which properties remain unchanged under each. Mobius is best known for the Mobius tip. Steinbabler was another contributor who introduced a new coordinate system in 1827-1828. The inventors of homogeneous coordinates, Feuerbach, Mobius, Babeler, and Plucker, used three coordinates instead of two locate points in a plane. Their systems were equivalent to trilinear coordination. Plucker initially defined these coordinates as distance from the sides of reference triangle and later gave the modern definition. Any triple related to Cartesian coordinates by and because multiplying all three numbers by the same constant give the same point. Homogeneous coordinates are not unique, but this causes no problems. Homogeneous coordinates naturally describe points at infinity, represented by triples of the form. This allowed earlier geometric ideas about ideal points and lines to be expressed numerically. In a triple, not all zero corresponds to a point, and any linear equation corresponds to a line. All points at infinity lie on the line, called the line at infinity. This coordinate system became especially powerful for the study of projective geometry. Plucker developed important formulas connected up plane curves, class order, and singularities, showing for example that a conic order 2 cannot have singular points. He later extended analytic geometry by introducing imaginary Cartesian and homogeneous coordinates with which made it is easy to explain results like Panselet theorem that all circles share the same two imaginary points at infinity. He also generalized the idea of Foxy for higher curves using imaginary tangents. Although France had been the early center of analytic geometry, Plucker worked shift leadership to Germany. However, he was not highly appreciated there because synthetic geometers like Steiner were more admired, and Jacobi opposed him. Discouraged, Plucker left geometry for physics in 1847 and made contribution to magnetism and spectroscopy. Plucker did not use determinants, partly due to conflict with Jacobi, which kept him from developing higher dimensional analytic geometry earlier. He nearly anticipated in 1846 by noticing that a line in three space can be described with four coordinates. Only in 1865 did he return to geometry and propose a four-dimensional geometry of space, where lines are fundamental objects. Meanwhile, Cayley had already begun the analytic geometry of dimensional space in 1843 using determinants and homogeneous coordinates. Written as is and left side is x, y, t, and x1, y1, and t1. X squared, y squared, and t squared equals 0. And in the right side, x, y, z, and t. xy, y1, z1, and t1. X squared, y squared rather, z squared, and t squared. And x cube, y cube, z cube, and t cube is equals to 0. Highly explained that in n-dimensional space, the basic n minus 1 dimensional element can be written using a determinant of order n plus 1 in homogeneous coordinates, just like in lower dimensions. Many geometric formulas from 2D and 3D extend naturally when written this way. In 1846, Cayley published work further extending three-dimensional theorems into four-dimensional space. A year later, in 1847, Cauchy always explored geometry in higher dimensions by introducing the ideas of analytical points and analytical lines in spaces beyond three dimensions.
Okay, this is the continuation of our report. So let's proceed into the non-Euclidean geometry. During the early 19th century, non-Euclidean geometry emerged almost simultaneously in the minds of three mathematicians from Germany, Hungary, and Russia. Gauss had realized that attempts to prove Euclid's parallel postulate were hopeless and that other types of geometry were possible, but he kept these ideas private. Meanwhile, the young Russian mathematician Nikolai Lobachevsky, 1793 to 1856, continued trying to prove the postulate. Through this effort, he eventually created a completely new geometry, which is called Lobachevskian, which is the hyperbolic geometry, which showed that Euclidean geometry was not the only truth. His ideas were evolutionary, but his colleagues did not recognize their importance. Leaving him to work largely alone, Lobachevsky discovery developed gradually. In 1823, he noted that no one had found a strict proof of the parallel postulate, though he had not yet rejected the possibility. By 1826, he presented a paper at Kazan University containing many of the new geometry mains theorems. This year is considered the unofficial beginning of Lobachevskian geometry. In 1829, he published these ideas publicly in an article titled On the Principle of Geometry in the Kazan Messenger. Between 1826 and 1829, Nikolai Lobachevsky became convinced that Euclid's fifth parallel postulate could not be proved from the others. In 1829, he introduced a new geometry based on a different assumption. Through a point outside a line, more than one line can be drawn that does not meet the given line. This became the first published non-Euclidean geometry, which he called imaginary geometry. Lobachevsky understood the importance of his discovery and wrote three major works: The Subjects, New Foundation of Geometry, 1835 to 1838, Geometrical Investigation on the Theory of Parallels, 1840, and Pangeometry, 1855. Gauss learned of his work and admired it privately, recommending Lobachevsky for membership in the Göttingen Scientific Society in 1842, but he did not publicly defend it for fear of criticism. Meanwhile, in Hungary, Farkas Bolyai spent much of his life trying to prove the parallel postulate. When his son Jonas Bolyai became interested in the same problem, his father warned him to stop, fearing it would consume his life. But Janos continued and independently reached the same conclusion as Lobachevsky around 1829, creating his own version of non-Euclidean geometry, which he called the absolute science of space. His work was published as an appendix to his father's book Tentamen. Riemannian geometry. Bernhard Riemann, 1826 to 1866, revolutionized non-Euclidean geometry, giving it a broader meaning. A mathematician from a poor family who studied in Berlin and Göttingen, known for his complex functions, including the Cauchy-Riemann equation and Riemann surfaces. Riemann's groundbreaking lecture, 1854, presented a lecture called On the Hypothesis which Laid the Foundation of Geometry. Introduced a new way of thinking about geometry. Geometry should study manifold space with any number of dimensions. His ideas were more general than earlier non-Euclidean geometry, which focused on parallel lines. Demonstrated that geometry does not have to deal with ordinary points and line. It can describe any spaces made from ordered sets of numbers following certain rules. So the key principle of Riemann geometry deals with finding the distance between 2 points are infinitesimally close together. In Euclidean geometry, this metric is given by ds dr plus dy plus d. But in Riemannian geometry, many other formulas can be used as a distance formula. Geometric use that determines of properties the space of other or the geometry. A Riemannian space is a geometric space whose distance formula, which is called the metric. It is defined by a function that many depend on the coordinates. Ordinary Euclidean space is a special case where this function takes simple constant values. The curvature and geometry. Riemann expanded geometry by deriving curvature directly from the metric. The term Riemannian geometry often describes spherical geometry, where straight lines are great circles and triangles sum to more than 180 degrees. This contrasts with the geometry of Lobachevsky and Bolyai, where triangle angles sum to less than 180 degrees. Using Riemann's name only for spherical geometry overlook his broader contributions, including his initiation of the study of general curved spaces. Riemann made contributions to physics, succeeding Dirichlet or Göttingen, demonstrated that spherical geometry provides a consistent model for a type of non-Euclidean geometry. Eugenio Beltrami showed that a surface called the pseudosphere served as model for hyperbolic geometry because it has constant negative curvature. A sphere has no constant positive curvature. If straight lines are defined through 2 points on the pseudosphere as the geodesic through the points, the resulting geometry will have the properties resulting from the Lobachevsky postulates. The plane is a surface with constant zero curvature. Euclidean geometry can be considered an intermediary between the two types of non-Euclidean geometry. Spaces of higher dimension. Spaces of higher dimension. Riemann's work unified geometry on a small scale, differential geometry, but analytic geometry on a large scale remained mostly unchanged until Plancke revived interest in it. After a long pause in publishing, Plucker returned in 1865 with new ideas, supported by Cayley in his later work, especially Neue Geometries des Rhomes 1868. Plucker proposed a major conceptual shift: space does not need to be viewed as made of points. It can instead be considered as composed of lines or other geometric elements. He argued that the dimensionality of a space depends on the number of parameters needed to describe its fundamental elements. For example, if three-dimensional space is treated as a collection of linear rather than points, it becomes a four-dimensional line space. Cayley extended this reasoning by interpreting the ordinary 2D plane as a five-dimensional space, whose elements are conic sections. Plucker introduced new terminology for this higher dimensional line geometry. A single equation in line coordinates defines a complex, two equations define a congruence, and three equations define a range. He discovered that quadratic line complexes resemble quadric surfaces, but his study was unfinished due to his death in 1868. His students, Felix Klein, completed the publication of the second volume of Plucker works for the following year. So let's proceed to the Felix Klein. Originally Plucker's assistant at Bonn, continued the development of analytic geometry, but in a new direction. Influenced partly by his visits to Paris, where group theory had become a major field, Klein recognized the power of the group concept to unify the diverse results emerging in geometry and algebra. So the group theory foundation. A group is defined as a set with an operation that is closed, as an identity element includes inverses for every element and obeys associativity. The elements may be numbers, points, or geometric transformation. The operation may be arithmetic or geometric. This generality inspired Klein to use group theory as a foundation for understanding geometry. Erlanger Program 1872, Klein proposed that each type of geometry can be characterized by the group or transformations under which its properties remain invariant. Geometry becomes the study of invariance of transformation groups. For example, Euclidean plane geometry concerns properties such as distance and area that remain unchanged under the group of rigid motions, translation and rotation of the plane. This provided a unifying framework for classifying all geometries through their underlying transformation groups, where AE, BD is equal to 1. This formed the elements of a group. The operation that combines two such elements is simply that of performing the transformation in order. It is to see that if the previous transformation is followed by a second. So here is the transformation of geometries. The result of two operations performed successively is equivalent to some single operation of this type that will carry the point x and y into the point x raised to the 1 and y raised to the 1. The operation of this type that will carry the point x and y into the point x raised to 1 and y raised to 1, if in this group, one replaces the restriction that AEB D1 by the more general requirement that DEBD is not equal to 0, the new transformation also form a group. Lengths and areas do not necessarily remain the same. A conic of a given type, ellipse, parabola, or hyperbola, will, under these informations, remain a conic the same type. Such transformations earlier studied by Mobius are known as affine transformation. This characterizes a geometry known as a fine geometry, so called because a finite point goes into a finite point under any such transformation. Euclidean geometry, in Klein's view, is only a special case of a fine geometry. A fine geometry, so it is in its turn becomes only a special case of a still more general geometry, projective geometry. A projective transformation is described.
It is clear that if D equals 0 and F equals 1, the transformation is affine. Interesting properties of projective transformation include the fact that 1. A conic is transformed into a conic, and 2. The cross ratio remains invariant. The work of Klein is in sense fitting climax to the heroic age of geometry, for he taught and lectured for half a century. So contagious was his enthusiasm that some late 19th century figures were willing to prophesy that not only geometry, but all of mathematics ultimately would be contained within the theory of groups.
So the last topic is post-Riemannian algebraic geometry. In the late 19th century, several new forms of algebraic geometry emerged, all deeply influenced by Riemann's work, especially his theory of complex functions and the concept of Riemann surfaces. While Riemann's geometric writings were important, it was his complex analysis that most strongly shaped these developments. Alfred Klebs played a central role in applying Riemann's ideas to geometry. Influenced by the Königsberg School and connected to Jacobi's lineage, Klebs began by using Riemann's complex function theory to study algebraic curves. His work led to significant results, such as classifying curves by genus and studying curves of the same genus with different branching behaviors. Klebs then collaborated with Paul Gordon to rebuild abelian function theory on an algebraic geometric foundation. Gordon, a leading figure in variant theory, influenced later Italian geometers such as Castelnuovo, Enriquez, and Savary, who relied extensively on invariance in their algebraic geometry. Klebs also explained his work from curves to surfaces, using double integrals to imitate the behavior of abelian integrals. With contributions from Cayley, Max Noether, and Zooten, and expanded later by Emile Picard and Bepo Levy, this direction produced some results, but ultimately proved limited because of the complexity of surfaces. By the 1920s, these geometric approaches gave way to a purely algebraic approach to algebraic geometry, more abstract, general, and ultimately dominant for several decades. So that's all. Thank you.